Right. Okay. So this is recording. Let's go to in class assignment 3 then. Um, Let me just quickly share it with you all. So a Chrome tab, or let's just do the entire screen. Um, are you all able to see it? It may not work. Are you all able to see what's happening on my screen now?
Yes.
Yeah.
Okay. Right. So, and can you now see the in class assignment?
Yes.
Okay.
Yeah.
Which question were you having problems with? Which one would you like me to start with? Any particular question?
The first one.
Okay, so here this was all to do with. So what we reviewed in the class on Monday was to do with centripetal acceleration and your torque, right? So we talked about two concepts. The formula for centripetal acceleration, AC, let's call it. Is that visible? Let's just do this. AC is equal to either the tangential speed divided by the radius, or it's equal to r omega squared, whichever one you want to use. Now, in this case, for question one, it says that the girl sitting on the tire that is attached to an overhanging tree limb by a rope. So the girl's father pushes her with a tangential speed of 2.5 meters per second. So we know our tangential speed in this question right here. So Vt is equal to 2.5 meters per second. And the diameter is 4.2 meters, right? So the radius is going to be 4.2 divided by 2. And that's going to give you, well, 2.1 meters, right? So now
Right.
you can find centripetal acceleration as Vt squared, because this is all the information that we have. So you can use this at 2.5 squared divided by 2.1. And that's going to give you 2.5 squared divided by 2.1, 2.98. Oh, sorry, yeah, 2.98. And the units are going to be meters per second squared, right? Does that make sense?
Yeah, I just switched the numbers around.
Okay. Most likely the error would have been here that you forgot to convert the diameter back into radius. But
Yeah.
um,
Yeah, I think that's what I did.
okay. Now for the second question, you've got that a dog is sitting on a 1.5, or it's sitting 1.5 meters from the center of the merry-go-round. If the dog, it should say dog here, if the dog undergoes a 1.5 meter per second square centripetal acceleration, what is the dog's linear speed, right? So linear, remember, linear was what? Linear is in a straight line. Tangential speed, when you're moving in a circle, the tangential speed is actually linear speed because it's speed at a given point, right? So it's asking for two things. Well, you've got r is 1.5 meters, and you've got a centripetal acceleration of 1.5 meters per second squared, right? The first part is asking you, well, what is Vt equal to? So, again, looking at this formula right here, AC is equal to Vt squared by R, and then this can be transformed into, well, Vt squared is equal to AC multiplied with R, or Vt is equal to AC R radical. Since your radius is 1.5 meters, AC is 1.5 meters, you're going to have 1.5 squared under the radical. The radical cancels out the square, and you've got a 1.5 meter per second tangential speed. Right?
Right.
Any questions with this?
So that's what the VT would be, 1.5.
Yep.
Okay.
Right, and you can do that too. You can multiply it 1.5 times 1.5 and square root that answer, and you should still get 1.5. Now, for the second part of the question, which is asking you for, well, what is the angular speed of merry-go-round? Remember, the other formula for centripetal acceleration is r omega squared. So AC is equal to r omega squared. Now, AC is 1.5. R is 1.5 times omega squared. 1.5 and 1.5 cancels out, and you get 1 over here. So your omega squared is equal to 1, or omega is equal to 1 radian per second. Does that make sense?
I have a question. So
Yes.
when you were finding like the linear force, how did you get the r equal to the square?
R equal to the square. Over here?
Yeah, like it's yeah.
So it's just that you can do 1.5 times 1.5.
Oh, because the r equals 1.5. Okay,
Yeah.
I got it.
Mhm.
Thank
So
you.
the speed, the acceleration and r are both 1.5. So I just squared them to get rid of the radical. Right?
Yeah.
Third question is, well, you've got a piece of clay that's sitting at zero point 0.2 meters from the center of Potter's wheel. If the Potter spins the wheel at an angular speed of 20.5 radians per second, what is the magnitude of the centripetal acceleration on the piece of clay? Right? Or off the piece of clay on the wheel. So again, your centripetal acceleration is r omega squared based on, well, what information we have, because we've got an angular speed. We can only use this formula. So it's going to be, well, 0.2 meters times 20.5 squared. Right? And that should give you 84.05 meters per second squared. Right? Any questions with that one? By the way, this is being recorded, so once we're done with this lecture, I'll process the video, post it on YouTube, and once it's processed there, I'll share the link on Classroom. So you will have access to this as well.
I have a quick question. So
Yeah.
for the first quarter, like kind of like first semester, you said we could redo any of the assignments like as many times as we want. Are we still able to do
Yes,
that?
yes. The same rule still applies. That same rule is still applicable. So all the assignments that have been handed back to you, you can redo those and hand those back to me. Once I'm done with grading most of the assignments that you've handed to me, I'll start going back and reviewing all of the assignments that you've redone. Right. Any questions with the 3 questions that we've done so far? No?
No.
Okay. Thanks. You'll have to keep telling me because I can't switch back to the window again. It may crash the Chromebook, so I'm not so sure. I'd rather not do that then. So you'll have to keep telling me. If there are no questions, then let's start with number 4. So you've got a torque required to loosen the nut on the wheel of a car has a magnitude of 40 newton meters. So you know the torque that is required. Torque is given by this little symbol right here, which is known as tau, or the Greek letter tau. 40 newton meters. That is your torque required. And then you know the lever arm right here, right? So you're looking for the minimum force. D is 30 centimeters or 0.3 meters. It would be it's best, or it's I'll recommend that you convert everything while you're taking down the data. So once you plug it into your formula, where for torque is what product of force times the distance, and remember the force must be perpendicular to the distance. This is a symbol for a perpendicular. So you've got torque, which is 40 newton meters times, or is equal to force times 0.3 meters. Or force, in other words, it's going to be 40 divided by 0.3, and that's going to give you, I believe, 130 something, 133.33 newtons. Since there's no direction specified here, right, we're going to assume that was a clockwise rotation, or sorry, counterclockwise, and take it as positive, right?
Mhm.
For question number 5, okay, so this may have been a little tough one. So what you have here is a simple pendulum that consists of a 3 kilogram point mass hanging at the end of a 2 meter. So this should be hanging at the end of a 2 meter long light string that is connected to a pivot point. Calculate the magnitude of the torque due to the force of gravity around this pivot when the string makes a 5-degree angle with the vertical. So now we can start with, well, first doing a little diagram. So let's say this is where the string is originating from, and you've got this little pendulum, right? Now the pendulum has a mass of 3 kilograms, so that would give you 3 times 9.81, which is going to be equal to 29.43 Newton weight acting downwards, right? Now it's also given to you that it's making an angle of 5 degrees for part A, right?
Mhm.
So now the good thing about vectors, if you recall, was that you could translate them. So now I can move this angle over here, or this force here, and by trigonometric properties, this angle is also 5 degrees, right?
Right.
I could also do, because what are the forces then acting on this? I'll need to define a frame of reference. Well, one force is going to be
Gravity.
acting towards the direction of the string, and the other one is going to be acting downwards, or kind of in the motion path where it's going to rotate, right? Because this is going to be the rotation factor for the pendulum. Does that make sense?
Yes.
So you've got W here, which is equal to 29.43 newtons. Again, by trigonometry, this angle is going to be 5 degrees. So now you can find the force components. You could have, well, a y component of the force and an x component of the force. Now remember, torque was what? Torque was that the force must be acting perpendicular to the lever arm, right? So we're looking for this force now, right? So your torque formula then changes to, well, Fx times the distance, or the lever arm. Now Fx is then going to be W. This is your W right here, this little vector right here. This is W, and sine of your angle theta, or 5 degrees, times your distance. In other words, you've got 29.43 once you put in the values, sine of 5 times the distance, which is 2 meters, right? And that should give you an answer of sine 5 times 29.43 times 2, 5.13 Newton meters, right? And then for part B, essentially it's the same formula that you're using. The only thing that changed here is that the angle has changed to 15 degrees. So now torque is, again, the formula still remains the same. For this case, that you're going using the force in the x direction, you've got fx d or w sine theta d or w sine 15 times d. Once you plug in the numbers, 29.43 sine of 15 times 2, that should give you an answer of
15.23.
15.23, yes. 15.23 newtons meter. Right?
Right.
Does this make sense?
Yeah, that makes a little bit more sense.
Right? So it's all to do with, well, remember, with the little diagram that you had for the wrench, I can't make that diagram very well. But essentially, whenever we're talking about the force, you're going to be doing, or torque, if this is the force, this is the distance. If the so this these must be perpendicular. If your force changes to, well, let's say this one, then you need to account for the angle. So if this is the angle that's the new force is making, you're going to be taking, well, the vertical component of this force, right? Or F sine of theta would be the one that you use in the torque. Okay,
Gotcha.
right? And remember, when we're doing this, if somebody asks you what is the work being done, if this force, the horizontal component of this force, so this blue one right here, the this is Fy, Fx would be the one that produces work done, which would be F cosine theta, only if you had a distance that would move, and that would be different than this distance because this is here the lever arm. So you just need to kind of take a mental note of these things. Right?
Right.
Okay. Any questions with this in class assignment?
Mm-mm.
No? Do you want me to move on to the review problem then?
Sure.
Yes.
Okay. Do you want me to go over all of this, or would you like me to go through a few questions of your choice?
You go over all of it.
Sure. So I'll start asking the questions, and you'll have to tell me what are the answers or what you think the answers were. Is that okay?
Yeah.
Okay. So for question one, what did all of you write or selected?
Isn't
I
it B?
put B.
B.
So I've got two options for B. What about the others?
I said B.
Yeah. Okay. So well, B is the correct answer there. Why? Because it's ampere. If you go back to your chapter one and look through those base SI units, ampere for current was the base unit, and Kelvin was for temperature. Right. What about question number two?
I'd B.
Okay. So if you were to do what are the units for speed? Meters per second, right? Now on this side you had meter per second squared, right? Divided by meters, or for height, right here, and that would under the radical, and that would change to L meter per second squared multiplied by 1 by meter under the root. Meter cancels out, so 1 by a second. That is your answer, which doesn't match with the left hand side, so this is not the right answer. Do you know what the symbol is? This one that I just circled.
Density.
Yes. So now you had to kind of repeat it for all of these. So let's do it for C. Option C, you've got V is equal to rho GH under the radical. So you've got kilograms per meter cubed times meter per second squared times meter under the radical. So you've got this meter cube would cancel out with this meter, and you'll be left with, well, kilogram meter second squared under the radical. So this is not the option because velocity here is meter per second. So we've got an extra unit of kilogram. For part D as well, you had meter per second here, and then meter per second squared divided by kilograms per meter cube under the radical, or meter per second squared multiplied by meter cube per kilogram. And since we've got this kilogram term that we can't get rid of, this isn't the correct option either. So the only thing that you're left with is option A, which is the correct one. And lambda here is usually the wavelength of a wave, which we'll talk in the next chapter. Right? But you could have deduced it after going through all of these for options B, C, and D, because none of these were the correct answers, and the only answer was for A, where you've got meter per second is equal to meter per second squared for gravity times meter, because it's the wavelength. Length has a scale of meter. You've got meter squared per second squared under the radical, or meter per second. That was the correct answer. Right?
Right.
What about question number 3?
I said B.
Yeah, I said B.
X
I
minus
said
y.
B. Would
What?
it be A?
Let's see. What is A? You've got Z plus X is equal to Y. Remember the vectors, you've got the head to tail rule. So in right angle triangles, like part A and part B, you can apply the Pythagoras theorem. And by squaring them and adding them together, you get the hypotenuse. If you were to simply add the vectors, and have you done vectors in maths now or no? Please remind me.
We're doing that next semester because I have pre-calc next semester. So if you would have taken pre-calc, I think you already would have done it.
Okay, maybe that's the reason why. But essentially, the quantity with vectors is. So I'm sorry I included this question then, but I'd assume that you'd done vectors. But essentially, the quantity with vectors is that if you were to you follow the head to tail rule. So in this case, for part A, you've got Z plus X, I'm drawing bars on top, is equal to Y. So these are going to be added, and Y is going against these two arrows, right? So you write that equation as this. Whereas on this case, or on the case of B, you've got, well, Z plus Y is equal to X. Right? So then the question is asking you, well, what does X minus Y get you? The answer would be, or Z shows the magnitude of X minus Y, and B would be the correct answer. Because if you were to rearrange this equation, Z is equal to X minus Y. Right? Whereas in this case of A, you would have Y minus X. In the case of C, you would have Y, so this one, because you've got this direction, and in that direction you're adding X to it, and that would equal to Z because this is counteracting to all of these directions, right? Similarly, in D, you've got Z plus Y is equal to X. Right?
Mm-hmm.
question 4. Right, so now you've got a student that is measuring a time t for a ball to fall from rest through a vertical distance h. Knowing that the equation is h is equal to half gt squared applies, the student plots the graph shown. Now, the thing to notice here that you've got h under the radical here, and you've got time here on the x-axis, right? Now, which of the following is an explanation for intersect on the t-axis? What did most of you select?
I said B. I also said B.
I said B too.
Okay. And I believe B is the right answer. Why? Because, well, think about it. What is happening here, you could rewrite this equation. H is equal to half gt squared as well. This is a constant value, right? This wouldn't change. So you could say that H is equal to, well, half g times t. Whatever is happening here is going to be shown in H, or the time factor is being multiplied. That doesn't change. So if t is equal to 0, H should be 0. So the only explanation there is that there's a constant delay that is happening between the timer and releasing the ball. Right? For part 5, what answer did you write?
I said B.
I said B.
B.
Okay. Why B though?
The acceleration, so Y. Part of the graph.
Right, so the question is saying that which graph represents the motion of a car that is traveling along a straight road with a uniformly increasing speed. So your speed is increasing, right?
Yeah.
If your speed is increasing, then what should happen to the acceleration, or what does that mean for acceleration?
It's increasing.
Is the acceleration increasing, or is it constant? Or is it a constant non-zero value? Think about it again. Remember when we done the little car example in class for chapter 2, where the car accelerated from, well, the start position to 400 meters across? We had, well, what happened? This was our displacement. If the speed was constantly increasing, this was our speed as well. So v against time. And the slope of these lines would get you what? The slope of a velocity, a constantly increasing velocity, would be a single number, right? And that single number, if you were to plot it against time, would be a straight line. So the answer here would be A and not B.
Yeah, I see.
Does that make sense?
Yeah, that makes sense.
Yes.
Okay. Because if you were to increase, if your answer was B, what's essentially happening is your acceleration is increasing, so your velocity is not increasing at a constant rate. Your velocity wouldn't do this thing. Rather than your velocity is actually doing something like this, right? Because acceleration is increasing according to this graph, and your velocity will be increasing more and more as the time goes on, because your acceleration is not constant. So B cannot be the right answer, right? For D, since displacement is not changing, that means your V is equal to 0. The car is not moving. For C, that's a normal figure that you start with some displacement that's increasing. That means that you're moving at V. But because this is a straight line and it isn't changing, that means that your speed isn't changing and you're moving with a constant speed. So if you were to take the slope of a displacement time graph, that would give you a straight line again on a VT plot, right?
Right.
So that's the answer to part or question number 5. What about question number 6?
I put D.
Okay,
Yeah, I wasn't really sure, but I just put D, but I don't know if that's right.
so what's happening here? What you see here is that this quantity, whatever this quantity is increasing, and then it kind of becomes a constant value at this point, right? So if you were falling, and y would be the distance, no matter what the air resistance is, your value would still increase for distance. It wouldn't become a constant value. So A and B, they're not correct. They're incorrect options. Now, y is the speed, so you're only left with C and D. So y is speed and air resistance is negligible. If air resistance is negligible, that means there's no drag, and you would be, because gravity is acting on you, your graph would be like this, or it would be a straight line. So your option C is not correct either. The only option is D, and that's because, and this factor is known as your, if you recall, we briefly talked about terminal velocity during one of the lectures, and that says your terminal velocity, or the object here has reached terminal velocity, that it wouldn't increase, or your gravitational acceleration is being matched by the air drag in this case, right? So D is the correct answer for question number 6. What about question number 7?
I said B.
Okay. What about others?
I also said B.
Okay. So
I did
remember,
A.
okay, we've got an A, we've got a few B's, right? So read the question. You've got a stone that is thrown upwards from top of a cliff. After reaching its maximum height, it falls past the cliff top and into the sea, right? The graph shows how the vertical velocity v of the stone varies with the time after being thrown upwards. So what happens once you were throwing an object upwards, you're moving it, or you're throwing it with a constant velocity, or with some velocity, not a constant, but with some velocity, right? Now gravity is going to act against it, and it's going to start slowing it down, right? So you threw the stone with some velocity right here, this blue dot. Now, once the stone left your hand, it's going to start slowing down because gravity is acting on it. Once it reaches its maximum height, what happens at maximum height? Your velocity changes to 0, right? So there's your velocity change to 0. Now it starts to fall back down again, and it keeps falling down until it impacts the water and the velocity rises back to 0. Right? So now in this case, this is the distance, or this is the area under the curve here would give you the maximum height. R, on the other hand, is your downwards falling distance. So the correct answer here was R minus S. Why? Because this is the total distance of the fall back down to the sea, and S is the rise of height, or the gain in height. So R minus S would give you, well, what is the actual cliff height? Does that make sense?
Yeah.
Yes.
So D was the right answer there. What about question number 8?
Isn't it C?
Well, would it be?
I said D, but I don't think that's right.
The total kinetic energy before impact is 0. Right. Let's see what happens. Are these two objects moving in opposite directions before collision?
No.
Well, look at the velocity directions. They're moving in opposite directions, right? One's moving
Oh,
towards
yeah.
the right, the other one's moving towards the left. So if you've got kinetic energy before impact, so that would be half mv, let's call this object 1, mv squared, right? Plus, let's call this object 2. They're all equal to each other, by the way. M1 is equal to M2, V1 is equal to negative V2. Let's just do that. So half M2V negative V2 squared. Because you're squaring it outside, negative would change, and what you would get is half mv1 squared plus half m2v2 squared. And your answer would be, well, because they're all the same thing, mv squared. So option C is incorrect. The total momentum before impact is 2mv. Again, what is momentum? mv, and it's a vector quantity, right? And you have to take into account, well, the direction as well. So you've got mv for this object right here plus m negative v. So this would be 0. So option D is incorrect too. Because it's a head-on elastic collision, and it's an elastic collision, option A does not, you cannot select option A because they won't stick and they would move away. The only option is, well, option B, that the total kinetic energy after impact is mv squared. Right?
Right.
Again, you've proven this. The kinetic energy is conserved in elastic collisions. So if this is your elastic potential, kinetic energy, total kinetic energy before impact, mv squared, it would be the same after the collision as well. Right? Any questions with this? No? What about question number 9? What answer did you select? Did you all select? Did no one attempt this question?
I think it's B.
B is the correct answer. Well, any other guesses? Somebody selected anything else? No? Well, let's have a look. F is equal to ma, or force is given by ma. Now, given you've got the acceleration and you've got the mass of the block, you can actually find the force that is being produced here, right? Because due to this acceleration. So 0.6 times 4 would give you 2.4 newtons. The question says that a 12 newton force has been applied, so that means that if you're only moving the block, or this block is being moved or accelerating to the 2.4 newton force, the rest of the force is friction force. So the force of friction then would be force applied minus force due to acceleration, right? And that would be 12 minus 2.4, and that would give you 9.6 newtons, right? Yes or no? Again, you need to tell me before I move on any further.
Yes.
Yes.
Okay. For question number 10, what option did you use?
I said A.
I had A too. Yeah.
Okay,
That was for me, A.
right. The correct answer is B. Why? Momentum is a conserved quantity, right? So that means m1 v1 plus m2 v2 is equal to m1 V1 plus M2 V2 after the entire thing happened and before, right? Now, so it says that the body was initially at rest, so this is all equal to 0. Now, and the other part that says here is that they move apart, so they're moving in opposite directions. So you can assume that M1 V1 is positive, M2 and V2 would be negative, and that's all equal to 0. And then it would be M1 V1 minus M2 V2 is equal to 0, or M1 V1 is equal to M2 V2. And then it's asking you for a ratio of V1 V2. So V1 divided by V2 would give you M2 over M1. And B is the right answer there. For question number 11, what did you write for the answer, or what did you all get for the answer?
I said D.
D is the correct one. And if you notice this little chart here, these are drawn to scale. So 4 newtons, you've got 4 boxes here. 3 newtons, you've got 3 boxes here. Now, if you look at this little vector here, 4 newton, which is going at an angle, you've got 1, 2, 3 boxes here. So you've got a 3 newton x component, and you've got, well, something here which you can find by Pythagoras theorem. So 4 squared is equal to 3 squared plus whatever this component is, let's say y, or y squared. Sorry, so y is going to be, well, 4 squared minus 3 squared under the radical, or under root 7 newtons. Right? And now since you're looking for the components of the force, you would do a force balance in the x direction. So 4 newtons minus 3 newtons that we've got right here on this side, that would give you 1 newton in the x direction, and sum of forces in the y direction. So you've got 3 newton right here for on the positive side, minus this root 7 newton on the other side, and I believe that gave you 3 minus root 7, 0.35 newtons. By the way, do you have time, or would you like to wrap up because we're out of time?
I have time.
Does everyone else too?
Yeah, I'm good.
Okay. Okay, so let's just quickly wrap this up then. So you've got 0.35 newtons here in the y direction, and because these are all positive, this would be in the positive direction. So D is the correct answer. Right? Because if you were to plot it like this is your positive y-axis, this is your positive x-axis based on this. And since both of the resultant forces are in the positive direction, this is the only direction that's in the positive, or given in the positive axis, or the positive quadrant. These are all in negative, so none of these would apply. Right?
Right.
Question number 12. What answer did you all get?
I got B.
What about the others?
So sure.
I've got 1B. What about the others?
I also got B.
Right. And B is the right answer. Right? So the only way you could do this as well, you've got potential energy at Q is 50 less than P. Right? So we're talking about the total energy of the system here. And at P, the kinetic energy of the trolley is 5 kilojoules. So we know that at P, the energy of the system was 5 kilojoules for the kinetic energy, and 50 more than Q. So your total energy was 55 kilojoules, and then you lost 10 kilojoules to the friction between point P and Q. So the total energy at Q would then be 55 minus 10, and that would give you 45 kilojoules. And that's your answer to part B. What about question number 13?
I said D.
D is the right answer. Anyone having a different answer than this?
Mm-mm.
Right? So power is what? Power was either energy divided by time or work divided by time, right? And what was work? Work was, well, force times the distance divided by time, and that would give you force times velocity if you took these two separately. So now you've got the force, you've got the total power. So 24,000 watts is equal to 600 V, or V is equal to, well, 40 meters per second. For question number 14, what answer did you all get? Was it simple enough? Yes or no?
I don't really understand this part of the worksheet.
Okay, so this is, rather than a multiple choice question, this was more of a, well, you had to tell me what was going on. So now here you've got that there's a steel ball of 73 grams held at 1.6 meters above a horizontal steel plate, right? And the question is asking you, well, calculate the speed of the ball as it reaches the plate. Now you could do it two ways. You could either do it using the equations of motion, right? And you've been given the distance, you know the acceleration, that is going to be 9.81, and the object starting at rest, I believe. It's starting at rest right here. So you could find Vf is equal to Vi. So you're using the third equation of motion, 2a delta x. So Vf is going to be, well, 0 squared plus 2 times 9.81 times 1.6. And your final velocity is going to be 2 times 9.81 times 1.6. And you take this radical of that, and that's going to give you 5.60 meters per second. So that was your answer to this part, right? So it was a simple free fall question, this one. For part B, you had, well, as the ball loses contact with the plate after bouncing, the kinetic energy of the ball is 90% of that just before bouncing. So calculate part 1, the height h to which the ball bounces. So you just found the velocity here just before impact, right? So you can find the kinetic energy just before impact. So Ke before impact is given by half mv squared. Half, what is the mass? The mass was 73 grams, I believe. Yes, so convert 73 grams into kilograms. So 73 divided by 1,000 times 5.6 squared. Or that would change to, or that would be 0.5 times 0.6 squared divided by 1,000, or 1.15 joules, right? Now 90% of that energy is remaining after the bounce. So kinetic energy after is going to be 90% of this, so 90 by 100 of Ke before impact. So times 0.9. So that is your kinetic energy after the ball is bounced, right? Now it's asking you for height. So the kinetic energy is now going to convert into what? Potential energy. So kinetic energy after is equal to potential energy, PE, or half mv squared after mgh, which we just found. So this is equal to 1.03 is equal to 73 by 1,000 times 9.81 times h. So this is going to be equal to 1.44 meters, right? And it should be less than 1.6 meters, which it is, right? Does that make sense?
Yeah.
And then the speed of the ball as it leaves the plate after bouncing, right? So we know, well, it left with this much kinetic energy. So kinetic energy was 1.03 joules, which is equal to half mv squared. So you can find the velocity through here, which is going to be, well, 2 times 1.03 times 1000 by 73 under the radical. And that should give you, I'm just rewriting this formula for velocity. And you should get an answer in as 5.31 meters per second. Right?
Yes.
And finally, question or part C is asking, well, use your answers in part A and part B to determine the change in momentum of the ball during the bounce. So delta P, it's asking you for change in momentum. MV final or after the bounce minus MV before the bounce. Right. So mass can be taken as common. Mass final or velocity final minus your velocity initial. Right? So we put in the numbers, 73 by 1,000. What is your final velocity that we just found? 5.31 minus 5.6. Should this be negative or no?
No.
Are you sure?
Yes.
That should be negative. Let me check quickly. I believe that should be negative, and you should get an answer. Well, what should your answer be then? So 5.31 minus, sorry, plus 5.6, that minus would change, times 73 divided by 1,000, 0.796 or zero point 0.8 Newton seconds. That's your answer. Right?
Yes.
Yeah.
Right? And what about answer to part D? What does the law of conservation of momentum tell you? That the net change in momentum should be equal to zero, or the loss in momentum here should be equal to a gain in momentum somewhere else. So this is the momentum that was lost by the steel ball, right? And if you look at the diagram again, right here, the ball bounced off of the steel plate. So this loss in momentum here is going to be, so the loss in momentum by the steel ball was the gain in momentum by the steel plate. Gaining momentum off the steel plate. And that's your answer. And the steel plate would move some, but essentially, because the steel plate is so heavy, you wouldn't really notice any movement in there compared to the steel ball. And that's why uh, you wouldn't notice it, but that momentum quantity is still conserved.
Gotcha.
Right? Plus, there are other losses as well because it lost some kinetic energy that meant that it was neither an elastic collision or it wasn't a a perfectly inelastic collision either. It was somewhere in between. So some of the energy was lost as sound, some of it was lost as heat energy and whatnot. But essentially, that's kind of it. Any questions with this?
Yeah, what was the answer to number 8? Sorry, my meeting disconnected.
Okay, question number 8. Question number 8 was the answer was B.
Okay.
Right? Remember, because the total kinetic energy before the impact is zero, that's not true because even though you took velocities into the directions into account, because you're squaring them, they're going to be still added together and you're going to left with mv squared as the kinetic energy. The total momentum, on the other hand, cannot be equal to 2mv because they're moving in opposite directions and that would reduce to zero right here.
Okay.
Yep, and since it's a head-on elastic collision, A cannot be the answer because they won't stick together. Any other questions? No?
No.
Okay. Okay. Well, let me stop